Hey, this is Horner, and this is the 1999 M1 question. In this lab experiment, you've got something called a ballistic pendulum. So they shoot a dart at a block, maybe a piece of styrofoam that's got a little bit of mass on the inside, and then this whole thing swings up and goes up to about here. And so they want to find out how fast this object is going. So they would probably commonly do this if they want to find out how fast a ballistic object is moving. So the dart is fired, and then it makes an angle, and the whole thing kind of happens there. So they want us to figure out what is the speed of the dart immediately before it strikes the block. And so to do that, we've got to do this in terms of little m, which is the mass of the dart, big M, which is the mass of the block, L, which is the length of the string, theta max, which is the biggest angle that this will make, and gravity. So pretty common thing for you to need to know how to do. So we'll go right through this and kind of see what happens. First thing that you should do on this one is think about the conservation of momentum. So we know that the dart is moving all on its own, so that's little m times VO should be equal to, and then together that would be m plus capital M, and then we're going to multiply that times our final velocity. So at this point our final velocity is equal to m times VO all over m plus MO. So why did we do that? Well, it's going to become apparent here when we go through the conservation of mechanical energy. So we know that kinetic energy plus potential energy due to gravity before should be equal to the final kinetic plus the initial kinetic energy. Initial potential energy after. We don't have any potential before, and all we have after is just potential. So now we can do 1/2, and this is the capital M, so this is the total mass times the final velocity squared, and that should be equal to the total mass times the gravity times the height that this goes. So when we look at this, we know that it's going to swing over, and so we want to find the height that it goes. So it's going to go from here up to about here, so we can kind of see that. So we're going to draw a line straight across, and now we have our triangle. The height that it will go is right here. And so we've got a triangle here, and then we've got this little extension on the triangle here. So to figure this out, what we'll need to do is we're going to say that if we do the, we know that this is L right here. And so we want this side, so we're going to cross the L off on this side so we don't get confused. So now we've got L on this side, we have an angle, and we want to know this side. So that would be the cosine of the angle. So this would be L times the cosine of the angle, but we just want this little part here. So we know that the entire thing is L. We remember that. So what we can do is we can say H is equal to L times, so we've got H, well, we need to have L all together. So we're going to take L minus, and then this would be L cosine of the angle. So if you factor that L out, what you'll end up with is H is equal to L times 1 minus, and then we just have the cosine of the angle. So that makes it a lot easier. So we know kind of what H is. So far we have earned 1, 2, 3 points. So this would be 1 point here, this would be a point, and then you get a point for determining what H is in terms of L. Now that we've done that, we've got to substitute everything into this equation. So this is going to be 1/2 of little m plus big M, and we'll go ahead and use big MO there, times our velocity. So remember, our velocity is here. So this is going to be m times VO over m plus big MO. And we know that we need to take that and we need to square it because that would be our speed squared. So it looks complicated. We're just filling things in. It's really not that bad. So this is equal to M plus big M-O. So there is our MT. And then G times whatever H is, and we said H up here is L times 1 minus the cosine of the angle. And I know, I'm sorry, I'm writing on this darker area over here. Now that we've done that, there are several things that we can probably go through and do and cross off. So one of those things that we can cross off is the M plus the MO. So you'll notice that we've got M plus MO here, and we have M plus MO here. So we're going to cross those off. Notice that this is squared, okay? So we are looking for, remember, let's go back to what we're looking for the original velocity. So we've got to get this guy all by himself. So to do that, let's go ahead and we're going to say M times VO over M plus capital MO. And we know that to get rid of the square, we're going to take the square root of both sides. We're also going to multiply both sides times 2. So this is the square root of 2 times G times L times 1 minus the cosine of the angle. And all of this is under the radical. And then we will have down on the bottom, well, you know what, let's not do that yet. We'll kind of take that off. Let's now solve for V. So if I put V here, that means this is equal to, I need to put M plus capital M-O times the square root of 2GL times 1 minus the cosine of the angle. And then that whole thing, let's just put this over M. So we really probably don't need to do that whole thing over M, so we can just do that much. That would be your final equation. So you've got 1, 2, 3. When you substitute in, you get a point, and then you get a point for the final answer, making sure that you've got everything in there correctly. And that would be the first several points. Let's go ahead and take a look at letter B. And in letter B, the dart and the block subsequently swing as a pendulum to determine the tension in the cord when it returns to the lowest point of the swing. So in order to do that, we're going to have to think about what's happening here. So I know that it's turning into almost a circle. So we know at some point we're going to have to think about circular motion here. We know that the sum of the forces should be equal to M times A. So mass times acceleration. So if we think about, we've got, here is our box, and it's down at the bottom, so we know that there's got to be a couple things going on here. One of them is I have mg, and then up I have ft. So that's the tension. So if I want to know this, I'm going to say T minus m total, so I'm going to put mt times g. So I took this, so this is the force of tension, minus mtg is equal to ma, and we're saying that up is going to be our positive. So that's equal to the mass total times A. So we're doing pretty well here. We know that A is equal to V squared over R because this is turning in a circle, so it's centripetal acceleration. So that's pretty important. Other thing we could do is we could also say that this is V squared over L because L is the length of the chord, which is also the radius. Now we've got our equation again. Let's go ahead and plug these things in. So we've got T minus mtg is equal to the mass total times V squared over L. Now that we've done that, we need to substitute everything into our equation. So let's go ahead and we need to substitute in for mass total and for V. So in order to do that, we're going to get M plus MO. So this is from earlier. So M plus MO times 1 over L times, and then we have MVO over, and then we've got M plus, now notice we're doing this side of the equation, so don't get confused, M plus capital MO, and we know that we have to square that. So our mass total is this guy, and then we said that we want v squared over L, so I did 1 over L. Instead I'm putting all this over L. That makes it a lot easier. And then that's equal to our tension, which is T, minus the quantity M plus big M O times G. So notice we've made the difference between small mass and the big block mass using this little O. That helps us if we get confused. So now we got to solve this whole thing for tension. Alrighty, here we go. So to solve this for tension, we have to add this thing to the other side. Okay, so now we've got M plus MO times 1 over L times MVO over M plus MO squared plus another M plus MO. And then we're going to take that times G. And so that now is equal to tension. If you leave it this way, you probably might get full credit. I doubt it, because they really want you to go through and cross some things off if you can. So what we're going to do at this point is we've got this thing squared, right? And so probably the best thing to do here is recognize that we've got to get rid of the square. We can get rid of the velocities right off the bat here. So we can kind of take a look at it. So let's do this. We know that this is going to be pretty complicated. So remember our VO earlier we said was this. So we're going to have to plug this in here. And then when you square it, it will square these things, and it will square this. And notice it's a lot of work. And so I wouldn't do it. But if you want to, in the end, you're going to end up with T is equal to M plus big M O times G. And then this would be 3 minus 2 cosine of the angle. I will tell you, they will take this. Because you have solved it for T. You don't have to simplify it. Makes it easier to grade, but in the end, they would take this. So that's disappointing, I know. Anyway, next thing. They say at your lab table, you have all of this equipment, and they want you to go through and design a practical method for determining the speed of the dart just after it leaves the gun, include the measurements you take and how that speed would be determined from that. So I will tell you probably the best thing to do is just go ahead and paste the answer in here. So that's essentially what I'm going to do. So this is worth 4 points, and they want the following: a practical procedure that uses some of all or all of the apparatus listed, recognition of any assumptions that has to be made, and then indication of proper mathematical computation. So they give you 2 points if the procedure wasn't complete but it did work, or if their math work didn't clearly specify all the variables. No points are awarded for a procedure that would not be feasible in a laboratory situation with this apparatus. So essentially what we're trying to do is we want the speed of the dart just after it leaves the gun. And I know that's kind of what we just solved for. But if you look at everything that's here, it says 5 more blocks of mass MO. You could go through and we could, so remember in this very first part what we did is we went through and we wanted the speed of the dart immediately before it strikes the block. If we want to find out what it is right when it comes out, since there was that distance there, probably the easiest thing to do is to take and move that apparatus so that now the end of the gun or the blow dart or whatever it is right up very next to the actual object itself. So that way when it comes out, it immediately embeds into here and then swings up. So we're getting rid of friction, air friction, by putting it right up next to it. So probably be the easiest thing to do. So you could basically just kind of go through and do the same thing, and they would take it. So the very last part of this one, and I'm going to get rid of this guy again here. There is one more part to this one, and the one more part to this one is not listed, and so that's good. But what it does is it essentially wants you to go through and find the acceleration. The only difficulty with this is you have to think about the you've got to think about the drag forces. So we're going to leave that one off for right now until we can do a better job of looking at drag force. And that is the end of this first problem, 1999.